You might remember that back in video 95, I told you that there were lots of different FET types with slightly different characteristics and that we couldn't reasonably cover them all. In this video, I'm going to give a general approach to FET amplifier bias design which you can apply to any type, and also have a look at some characteristics in a bit more detail. We've already discussed how FET operation can be represented by a graph as shown on the screen. In video 67, we discussed that for good bias, we want the output voltage of the amplifier, Vout, to lie approximately in between the supply voltages, the plus and minus supplies, when there is no input signal when Vin equals 0. This allows the output voltage to swing all the way from a positive supply to the negative one as it responds to the signal. With the ordinary transistor, or BJT, the strategy we adopted was to create a current flow through the device even when no input signal was present. This then enabled us to produce an output voltage at half the power supply voltage using a collector resistor. We can do exactly the same thing with an FET, but using a drain resistor. This time, to set ID, we must provide an appropriate voltage between the gate and source. Quite often, the current chosen is in the middle of a graph, as this is the most linear region. We'll look at this in more detail with examples in the next couple of videos. Before going to them, there's a couple of points worth noting, however. The first of these is the origin of the graphs that I've been using. These are often supplied with the FET, but can be easily generated from the general characteristic graph as shown on the screen. Secondly, you'll notice that the graph isn't a straight line. So like the BJT, the output current of a transistor is not linear with changing input voltage. In other words, in the equation ID equals Gm times VGS, the transconductance Gm is not constant. It changes in different parts of the graph. In the BJT, the relationship between IC and VBE was exponential, but in an FET, it's given by the equation shown on the screen. ID is equal to K times VGS minus VT all squared, where K is a constant and VT is the threshold or pinch-off voltage, where the FET stops conducting. The relationship here is therefore quadratic, that is, it contains a squared term. Like the BJT, if we want a nice linear amplification, we need to keep the input voltages small so that the graph looks roughly linear. Large signals will cause distortion and then clipping, just as they did with the BJT. Finally, we should note that some FETs don't need complex biasing at all. Take the p-channel depletion MOSFET. This has a characteristic graph shown on the screen. We can see here that a current flows even when VGS is equal to 0. So we don't have to do anything at all to bias a transistor and generate a current, except to tie the gate to 0 volts with a large resistor as shown on the screen. In the next couple of videos, we'll look at a couple of popular ways to bias various different types of FET.